Okay, so we're going to get started with proof now, and we're going to be looking at mathematical proof in particular. And where we want to start with proof is this idea of what a definition is from a mathematical perspective. So a definition is actually a very, very concrete statement. There's not a lot of vagueness in it. Unlike oftentimes with the dictionary where you'll have multiple definitions, in mathematics we generally will have one definition, and then from that one definition we get a lot of theorems and corollaries and all sorts of things that push off that definition. But that definition has to be very, very concrete, and that's for a logical reason. And that logical reason is that we need to be able to state that a number or value or an object that we're looking at is that thing or it is not. It's a true false. It's binary, right? It's a 0, it's a 1. Is it the thing or is it not the thing? And it all has to do with the logic of it. Okay? The logic of it, which is basically, if I have an if-then statement, a conditional, I need true implies true, okay? And I need to be able to prove that kind of thing. I need to develop valid arguments from a logical perspective. So my definitions must be very concrete. They are very clear, and there's no room for interpretation, okay? Now, there may be people who are like, oh, well, there's a little bit of room for interpretation. Maybe this thing has this quality, and it kind of doesn't. Well, for our purposes and for discrete mathematics, we're going to see a set of very common definitions, and we're going to stick to very, very closely their definitions. And we're going to utilize those definitions, and we're going to use them in order to be able to do proof. So let's look at some common definitions for discrete structures of discrete mathematics. And so the first one we want to look at is we're going to look at even and odd. And this is the idea, actually, we'll start out, it's called parity. And so parity is whether or not something is even or odd, and that is in fact integers. So it's going to be from the set of integers, and we're going to ask ourselves whether or not an integer is even or an integer is odd. We don't talk about non-integers from the perspective of even and odd. It doesn't make any sense, and you're going to see why in just a second when we get the definition. So if I have an even number, we're going to say that x is even if x equals 2k for k belonging to the integers. So if I can find an integer k and multiply it by 2 and I get back x, then x is even. Give you just a couple of examples of that so you can see exactly what that looks like. The number 4 is equal to 2 times 2. 2 belongs to the integers, so 4 is even. The number 3, okay, is actually equal to 2 times 0.5, or excuse me, times 1.5. But 1.5 does not belong to the integers, and so consequently 3 is not even, right? We're going to get another definition called odd that's going to help us out here, but because 1.5 is not an integer, that means that 3 is not even. One more example, we'll use like negative 6. Negative 6 is actually equal to 2 times negative 3. Negative 3 does belong to the integers, so negative 6 is even. So negative 6, 4, they're even. One other one you want to notice is that 0 is actually equal to 2 times 0, and 0 does belong to the integers, so that also means that 0 is an even number. Okay? This is our definition. X equals 2k for k belonging to z. So anytime we describe something and we say it's even, we know that we can do exactly this, that it follows that particular definition. What about odd? The definition of odd then is x is odd if x equals 2k plus 1 for k belonging to the integers. Now, by the way, I'm actually going to make this an if and only if, and I'm going to make this one an if and only if as well. And the reason why is that if this is true, that means that x is odd. And if x is odd, it means that x equals 2k plus 1, right? So essentially, we can actually write this as odd is defined as x equals 2k plus 1 for k belonging to z. And we'll define even as x equals 2k for k belonging to z. And those are our definitions. So you have one, you're going to have the other, right? And that's what we mean by that if and only if. So looking at odd numbers, let's take, for example, number 3. 3 equals 2 times 1 plus 1. 1, which is this number right here, belongs to the integers. Okay, so 3 is odd. We got 5. 5 is 2 times 2 plus 1. And that is 2 belonging to the integers. That's the number we multiplied by 2. There we go. Take negative 20. Negative 20 is, well, if we actually go in and we kind of do this, what you'll notice is that negative 20, that's even, right? Okay. Even. And since negative 20 is even, that is 2 times negative 10, right? For 10 belonging to z. Well, that actually tells me, in fact, that negative 20 is not, in fact, odd, right? And we could see kind of a similar thing if we kind of said, okay, let's like 2x plus 1 equals negative 20. Subtract 1 from both sides, and we get 2x equals negative 21. And so then that's going to then imply that x equals negative 10.5. But negative 10.5 does not belong to the integers. Okay? It does not belong to the integers. And so consequently, what we know is that negative 20 is not odd. These two are parities. They, in fact, are opposites. So what we can say is that a number is even, or excuse me, an integer is even if it is not odd. And an integer is odd if it is not even. The nice thing that we can do with something like that from a logical perspective is we could say, like, say for example, let's have a proposition, and the proposition is x is odd. If I negate that, if I negate x is odd, that actually translates to, that's logically equivalent to x is even. It's in fact the same statement. If x is even, then if I have this is false, and then we have not false, that actually means that that must be true. Okay? If, on the other hand, we have the other way around, and we have x is odd is true, then that means x is even is false. So those two end up being logically equivalent. Okay? So when we talk about parity, those are our two opposite ones, and these are our definitions. X equals 2k plus 1, and x equals 2k. The next definition I want to do is to define whether or not something is in fact a rational number. So what we're going to do here, and I'm going to write it in logic, this is going to be x is rational, or you know what, let's actually rewrite that utilizing our new notation. X belongs to the rationals, okay, if and only if there exists an x, or excuse me, there exists an a, and there exists a b, okay, a and b both belonging to the integers. These are both integers, such that a over b equals x, or x equals a over b. Okay, so we have a and b belonging to the integers, all right, and so there exists an a, there exists a b, such that a over b is equal to x, right? If I rewrote that, I would say x is rational if and only if x equals a over b for a and b belonging to the integers. And we actually have to have one more, and b not equal to 0, because we don't want to divide by 0. Okay? And b not equal to 0. So as long as b doesn't equal 0 and a and b are both integers, we have a rational number. Let's take a look at some examples. We'll take 1/2. So if we let x equal 1/2, then a will equal 1, b equals 2. They're both integers, and b is not equal to 0. So hence, x is rational. Let's take x equal to 3. And it may look like you're like, okay, well, 3, that doesn't look like a ratio of numbers, but actually it is. A is going to equal 3, and we'll let b equal 1. So this is 3 over 1. 1 doesn't equal 0, and both 3 and 1 are both integers, so hence x is a rational number. You could also, by the way, let a equal 6 and b equal 2, and those two numbers also work. It doesn't necessarily mean, when we read this definition, it doesn't mean that there's a unique set of values, okay? There could be a lot of different sets. Now, when we start doing work with like proof by contradiction, and we talk about the square root of 2 and things like that, we may want the values for A and B to be the smallest possible, the most irreducible values. But in this case, for our definition purpose, we're not going to need that. We'll talk about that a little bit more later. On the other hand, if I look at x equals pi is actually a problem. It's a non-repeating, non-terminating decimal. Non-repeating, non-terminating decimals you can't actually write as a ratio, and so consequently not rational. They're not, in fact, rational, or pi is not rational, okay? So it does not belong to Q. And there we go. Now, we've got this definition of rational, and one of the things about the definition of rational is that we'll have its opposite, okay, which is irrational. But an irrational number is defined in terms of the rationals, and you'll see that that's one of the reasons why we're going to use the proof methods that we have for proving something's irrational, okay, or proving something is rational. We're going to use certain methods, and the reason why we're going to use these methods is because there's a definition for irrational, but it's not like the one for odd and not like one for even. A number is irrational, right? X is irrational if and only if, okay, X is not rational. So if you wanted to prove, like say for example, we've got pi, and you want to prove that pi is in fact irrational, well, what do? You actually have to show that pi is not rational. Okay, you show that pi is not rational. So again, from a logical perspective, if we have, right, X is rational, that's going to be logically equivalent to X is irrational. It is either it is or it is not, and these two are in fact opposites. All right, and in the case of the even numbers, okay, when we want to think about the integers, an integer is either even or it is odd, okay, and a real number is either going to be rational or it's going to be irrational, okay. So even and odd is a way of breaking up the integers, and being rational is a way of breaking up the real numbers, okay. And in both cases, we're going to do this utilizing our definitions. And so just as a reminder, here's your definition right here, okay. X equals A over B, A and B belonging to Z. Now that we've established some baselines, let's take a look at some other definitions that have to do with, say, for example, the integers. So let's look at this idea of, or this definition for consecutive numbers, all right? Or we might actually more specifically and more probably accurately call them consecutive integers. So let's say, for example, X is an integer. The next integer is going to be X plus 1 is the next integer. So we'll start with X, it's some unknown, and X plus 1 is going to be the next integer. It is a consecutive integer, okay? So X and X plus 1 are consecutive integers. So for example, X, X plus 1, X plus 2, and X plus 3, those are also consecutive. That's 4 consecutive integers. Now, we can actually make this a little bit more tricky. Let's say, for example, we want 2 consecutive even integers. When I want to actually write 2 consecutive even integers, what I'm going to do is I'm going to say, okay, well, k is the integer. I got x equals 2k, okay? X equals 2k, and the next one is actually going to be, the one, call it y, is going to equal 2k plus 2. That's going to be the next value. So if x equals 2k, the next consecutive even integer is going to be y equals 2 times k plus 1 when I actually go in and factor. If we want to think what's the one after that, okay, we'll call it z is the next one. Z equals 2 times k plus 2. So in this case, we're going to iterate, okay, we iterate the integer. And what it means to iterate an integer is to basically do the next one, the next one, the next one in terms of plus 1 each and every time. So when we actually want to find consecutive even integers, we can theoretically add 2, that's fine, but most of the time it's probably cleaner and more effective for our proof processes to just take 2 times k plus 1, 2 times k plus 2, 2 times k plus 3, just like we did with our consecutive integers here. Think about it from the perspective of, let's say, for example, I want to do 3 consecutive odd integers. How I'm going to do something like that is it's going to look like this. It's going to be 2k plus 1, and then it'll be 2 times k plus 1 plus 1, and then it'll be 2 times k plus 2 plus 1. And you can imagine you can do that forever just by iterating each and every one of those integers. And so that's how we generate consecutive integers. Now let's look at another definition, and that's the definition of divisible. Now divisible we utilize a lot inside of number theory, and when we work inside of modulos and things of that nature. And so it ends up becoming very, very powerful when we work with discrete numbers. Now divisible actually has its own symbol, right? And so we'll say x divides y, and that's what we actually write here. We say x divides y, okay? Or we can also say that y is divisible by x. And that's what we're saying there. And the fraction sign or the slash is generally how we go about writing something as a division or as a fraction. And fractions basically are division. So we're going to see that symbol. And so we're going to say that x divides y if and only if there exists, and we're going to call it m belonging to the integers, such that y equals mx. So basically what we need to do in order to show that x is divisible by y is we're going to need to show that we've got some integer that I can multiply by x and get y back. So for example, if I let x equal 2 and y equal 6, then 6 equals 2 times 3, okay? And so that means that m equals 3, and what we say is that 2 divides 6. And there you go, 2 divides 6. That's it. Let's say, for example, we let x equal 1 and y equal 7. Then we get 7, our y is equal to 1 times 7. So m equals 7, and we say that 1 divides 7. Okay? On the other hand, if I said something along the lines of, let's let x equal 5 and y equal 12, well, in this case, 12 equals 5 times, and we think to ourselves, well, what would that be? That's going to be 12 over 5, okay, or about 2.4. But 12 over 5 does not belong to the integers. Okay, so what we end up with is that 5 does not, and we actually put that sign, does not divide, 5 does not divide 12. Which you probably already had the instinct about. What we want to get, though, is we want to get, here's our definition. That definition, that if there exists an m belonging to z such that y equals mx, then that means that x divides y. That's our definition. We're going to utilize that one. That's either true or it's false, right? It's either true or false. There we are. So the next one that we want to look at is this thing called the perfect square. And you probably know what perfect squares are, like 25 or 16 or 1, for example. The idea of a perfect square is x is a perfect square if and only if there exists an integer, and we'll call that integer k, belonging to the integers. Okay, there exists an integer k such that, right, what we end up getting is that k squared equals x. So we've got to be able to find an integer, and if I square that integer and I get x back, then it's a perfect square. So like, for example, all right, good example of this, 25. 25 is equal to 5 times 5. That works. And so 25 is a perfect square. Notice that 5 isn't the perfect square, 25 is the perfect square. On the other hand, negative 25 can't be created by multiplying two integers together. Negative 25 is not equal to a k squared, okay? Because then you're going to get k is going to equal the square root of negative 25, And the square root of negative 25 is not an integer. It is in fact a complex number or an imaginary number. And so consequently, not a perfect square. So negative 25 is not a perfect square. And that's our definition of a perfect square. Now the last one that I want to look at in terms of our definitions is this idea of we're going to do less than, greater than, less than or equal to, and greater than or equal to. Okay? So the reason why I bring these up, not so much because they have a very rigid definition, but to kind of get a sense of what each one's opposite is. Okay? So if we say x is less than y, right? We have x is less than y, and I wanted to go in and I wanted to negate x is less than y. That's actually going to be logically equivalent to x is greater than or equal to y. So notice that the opposite, okay, the opposite of less than is greater than or equal to. Because if we're going to actually go in and separate out all of our values into two separate groups, like either a true or a false, if we have less than, then the false would be if it's greater than or equal to, because equal to does not fit into the less than category. So one really important piece here, okay, is this does not include x equal to y. So when we actually go through and negate our less than, we're going to get, the negation of those is going to be the greater than or equal to. Also, if I negate x is greater than y, that's going to be logically equivalent to x is less than or equal to y. Okay, again, noticing that what we need to do is we need to include in that equals piece. So that equals piece is actually really important. Okay, and same thing, if I negated x is less than or equal to y, that's going to end up being logically equivalent to x is greater than y. So we go from having the equality part to not having it, to having it be a strict inequality. And the negation of x is greater than or equal to y is going to end up being x is less than y. Okay? And so for our last definitions here with this greater than or equal to, and that's our greater than or equal to, greater than, or actually let's just call them inequalities. For our inequalities is to remember that from a definition standpoint, okay, when we've got that true and false, the opposite, the false to less than is greater than or equal to. The false to greater than is less than or equal to, and that actually allows us to keep our relationships here very binary, just like they have been for every other one of our definitions. So that finishes up the mini lecture on definitions. Things to remember about definitions. Definitions are if and only if statements. We talked about that a little bit at the beginning, and what that means is that if I know that x is, say for example, is odd, then I know that it is equal to 2k plus 1 for k belonging to the integers. And if I know that x equals 2k plus 1 for some integer k, then that's going to give me that x is in fact odd. And so consequently, that's going to end up becoming really important and very valuable as we do proof. Secondly, we want to understand that definitions allow us to state that something either definitively is or it is not something. It doesn't. We don't want the shades of gray that we get oftentimes with definitions. We want to be able to say it is this or it is not that. And mathematically, that keeps everything very, very logical, right? It keeps it at the true, false level. Okay, so that's the second part. We want to make sure that we are either definitively saying it is a member or it is not. And then the third piece is to notice that our definitions, in fact, have, on the one hand, they'll have a true part, and then on the other hand, they'll oftentimes have a false part. Okay, so like if we want to say x is a rational number, the best way to say that x is irrational is to say that x is not rational. And so consequently, we have that binary relationship between a lot of our definitions, and this allows us to do a lot more with our proof work. When we start doing things by proof by contradiction or proof by contraposition, you're going to see that the ability to say that x is not something, meaning that x has a different definition, is going to come in very handy when we go through and do proof. So this finishes up the proof. We got even and odd. We've got rational and irrational. We have divisibility. We have the idea of consecutive numbers. We have perfect squares. And we have inequalities. So let's work on these. Go ahead and memorize them because they're going to come in very, very handy.